Quantum physics is a strange and fascinating world, full of unexpected phenomena and mind-bending concepts. It governs the behavior of the very small, the particles that make up everything around us. Think atoms and the particles within them, like electrons, protons, and neutrons, all dancing in a delicate balance. This realm is full of mystery, where particles can exist in multiple states at once. Our everyday intuition breaks down, and the rules of classical physics no longer apply. Quantum physics is like a new language with its own set of principles and equations. It takes time to understand its rules, requiring deep study and contemplation. But the journey is full of wonder, revealing the hidden layers of reality. Quantum physics is not just abstract theory, it has practical applications. It impacts our daily lives in ways we might not even realize. From lasers to smartphones, its applications are vast and transformative. Understanding quantum physics is crucial for the next generation of scientists and innovators. It helps us comprehend the universe's fundamental nature, unlocking the secrets of existence itself. Quantum physics introduces bizarre concepts that challenge our everyday understanding of reality. One of the most fascinating and perplexing of these concepts is superposition. Imagine a coin spinning in the air. As it spins, it's in a state of flux. It's neither heads nor tails until it lands and we observe the outcome. Similarly, a quantum particle exists in multiple states simultaneously, a phenomenon that defies classical logic. It's a blurry mix of possibilities, a superposition of states. This is the essence of superposition. Another strange and equally intriguing concept is entanglement. Imagine two coins flipping and landing the same way, always. They are inexplicably linked. In quantum entanglement, particles are connected in such a way that the state of one instantly influences the state of the other. Measuring one particle instantly affects the other, regardless of the distance separating them. Einstein famously referred to this phenomenon as spooky action at a distance. The uncertainty principle adds yet another layer to the intrigue of quantum mechanics. It states that we can never know both the position and momentum of a particle with perfect accuracy, a fundamental limit to our knowledge. It's like trying to pinpoint a wave's exact location in the ocean. The more we try, the more elusive it becomes. The more we try to define one property, the more uncertain the other becomes, highlighting the paradoxical nature of quantum mechanics. Quantum physics posed a challenge. It contradicted the established laws of classical physics. Classical physics governing the macroscopic world seemed deterministic and predictable. Objects had definite properties and followed predictable paths. But quantum physics threw a wrench in this neat picture. Imagine throwing a ball. In classical physics, we can predict its path. But in the quantum world, the ball's position is a blur of probabilities. It could be in multiple places simultaneously. This fundamental difference sparked debates and revolutionized our understanding of the universe. Section 4. The Einstein-Bohr debates, a legacy of disagreement. These debates were not just academic exercises but were pivotal in shaping the direction of modern physics. The conflict between classical and quantum physics ignited fierce debates. These discussions were intense and often passionate, reflecting the high stakes involved in understanding the nature of reality. Albert Einstein, a champion of classical physics, famously opposed some quantum interpretations. He believed in a deterministic universe where everything could be predicted if we had enough information. He argued against the probabilistic nature of quantum mechanics. To him, the idea that particles could exist in multiple states at once was unacceptable. God does not play dice, he famously declared. This quote encapsulated his belief that the universe is orderly and predictable. Niels Bohr, a pioneer of quantum theory, engaged in legendary debates with Einstein. Bohr's perspective was radically different, emphasizing the inherent uncertainties in quantum mechanics. Bohr argued that the fuzziness of the quantum world was fundamental. He believed that particles did not have definite properties until they were observed. He emphasized the role of observation in defining quantum reality. According to Bohr, the act of measurement was crucial in determining the state of a quantum system. Their debates shaped the future of quantum physics. These discussions laid the groundwork for many of the advancements in quantum theory that followed, influencing generations of physicists. Section 5. Quantum experiments, validating the incomprehensible. While the debates raged, experiments provided evidence. One famous experiment was the double-slit experiment. It demonstrated the wave-particle duality of light and matter. Light, thought to be a wave, surprisingly behaved like particles. This experiment challenged our classical intuitions and solidified the foundations of quantum physics. These experiments demonstrated the strangeness of the quantum world. They showed that quantum principles, though counterintuitive, accurately predicted experimental outcomes.